Today's lecture we're gonna discuss the last chapter of the textbook. So as you would see, this will discuss self-avoiding chain. A first look. Unfortunately, the textbook is written quite simple. You're not gonna get much out of it by reading that tiny chapter. So what I'm gonna do today is to explain to you in a little bit more detail what those what is the self-avoiding work is, and how does this help us to understand what is the real polymer chain inside a polymer solution. Okay, and I mentioned it quite a few times, as well as the model I assigned everybody to define, those free chain model, free rotation chain model, as a rotation isomer model, or only related to idealized polymer chain. And specifically idealized polymer chain, we specifically talks about that your polymer can walk on the top of each other, can sit on the top of each other. There is no exclusion volume effect. And this is apparently not real. And it does not fit into the picture that when you dissolve a polystyrene in a good solvent, let's say toluene or xylene, in those cases, people found what they measured, the radius of gyration, is much bigger than what they predicted in terms of degree of polymerization or molecular weight. This causes a question, people trying to understand why is the case and how can they make the model better. So that comes down to today's lecture. So today's lecture, we're going to talk about real polymer chain, something you can touch in the lab and something you can dissolve then and do measurement yourself. So what is it? So real polymer chain is a polymer dissolved in a good solvent. And the consequences with difference to the ideal polymerized chain is quite straightforward. You have a polymer has now received a lot of repulsive force between different segments. The repulsive force comes down to the horrible packing problem. If you have two materials trying to get closer and closer, at long distance you would have attraction force due to the gravity. Okay, so that's Newton's third law of physics, where you would have a lot of attraction force, and traction force will increase with the distance it's being decreased. Okay, so you can think about attractive force F, plot as distance R. That's just the distance between two objects. So you can imagine there's two circular balls. If they are far away, you would have some attraction force. It will increase. At a certain distance, it will reach a maximum, then transit to repulsive force. And why? Because it's just a horrible phenomenon that you cannot have two balls sitting on top of each other. You will generate repulsive force. Okay, that's the reason happens here. Same for the polymer chain. If they are too close to each other, they're going to have a certain repulsive force. And to address this, scientists have found another way to call it using another computer model. Remember what we discussed in the first case for free joint chain model, we used something called random walk. Okay? And what the random walk does is basically a way for you to visualize a material is moving around in a three-dimensional space, and it's freely. For real chain, we can also generate a computer model. This is often called self-avoid walk. So what does self-avoid walk mean in a layman's language? It basically says You can walk around like what we have discussed it before. You throw a dice, then you have the polymer move left and right, up and down. And if the polymer chain has already been to the lattice before, let's say now I throw a lattice, it asks me to go forward, and I throw it again, it asks me to go backwards. So when I return to original position, the computer says you cannot do that. You have to avoid what you have been there before. Okay? So this is basically the layman's language of self-avoiding walk. So you need to throw it one more time until you reach a lattice. It's not where you started off. And now it started to make better sense. Self-avoiding work would represent much better of what is real polymer chain in three-dimensional space. A real polymer chain is a self-avoiding chain basically in good solvents, because when you think about what happens is you have increase of degree of polymerization. You have to keep increasing the carbon bond. And next bond or next carbon atom will not reach back to where your original carbon atom is sitting, but it will go around to a different direction. And this self-avoiding work, what causes some effect that we talked about in the last lecture is called expansion, or increase the size of your coil. And we discussed the scale concept, and we remind everybody again. We already know that your polymer size will increase with number of polymer bonds in the backbone. That has been covered throughout this lecture. And for an ideal chain, we can generalize it end-to-end distance, or let's use Rg in this case, would be equals to 1 divided by 6 ml square. Or you can just written as mb square. In this case, you got m is b is statistical segment length. This is the repeating unit, and number of bonds, etc. And by now everybody should be familiar with it. And in the scale concept, we said we can use proportional relationship, saying Rg would scale with, this means scale, your Rg will scale with n power of 1.5. And we also alluded that if you consider a real polymer chain, that you would have basically an expansion of your polymer chain, right? We discussed this would be, let me see, how can I erase it? I'll just cross it out. It should be n 5/3, or this is 0.6. So you can see now your Rg at the same degree of polymerization will be increased, right? So we can throw in some numbers for everybody to understand. Your Rg, if n equals to 100, Rg will be proportional 10 times a constant x, let's call it. In the bottom case, you would have 10 to the power of 0.6. I don't have a calculator with me, but I can use my cell phone, quickly do the calculation for everybody. So this should be 100. So let's give it a try. 100 power of 0.6 would equals to 15.8 multiplied by x. That's quite a big difference, right? You are talking about here, it's more than 50% of expansion of the size in the polymer coil inside an idealized polymer chain versus a real polymer chain. So that is quite an important discovery people found when they measure the real polymer versus idealized polymer. And this comes down to why this is happening and why this is coefficient is only 0.6. It's not n equals to 1. And we sort of touched the base what is m power of 1, that will be a rigid rod. You basically have a strong polymer chain going all the way. So that will not fit into the real polymer chain model. So we know it's somewhere between 0.5 to 1, but why exactly it is 0.6 is what we're going to explain in today's class. So what kind of force you can think about for a polymer in a good solvent? What is restricting its expansion? What is promoting expansion? So let's say your real polymer chain is balanced by two forces. Okay, one is forces trying to make it expand more. One force is to make it contract, make it smaller. The other one to make it bigger. So by the end of the day, if these two forces balance out, that's where your equilibrium size. So think about what is the force can make the polymer expand. So this is comes down to Floria's theory. Remember that I mentioned this very famous polymer scientist was also a Nobel Prize winner. Back in 1950, did some very simple mathematics, figured out what would be the dependence of the polymer core size with respect to the degree of polymerization. So we're just going to go through what his journey about 70 years ago. So everybody thinks about what would be the expansion force. Can anyone make some wild guess? You don't need to get the answer perfectly correct. Yes, so if the chain repulses itself, that's perfect answer. Okay? So how do we quantify it? So we can think about chain repulsion where two chains must be touching each other, right? So what it would be possibility of one chain touching each other is a very important concept here. That comes down to the volume of the polymer. Okay, we need to consider what's the density of the polymer. Because think about if we are iron sort of a polymer chain sitting inside a large classroom versus a compact classroom, my chances of meeting another people is low versus meeting another people is high, right? So if you're talking about a population in a small town, in Hattiesburg, we got about 50,000 in the city limit. Your chance of meeting a people is equal to how many people in that real estate divided by the area of that. That is true for the polymer in three-dimensional space. So repulsive force would be equals to how many polymer chain you have inside system, okay, and it's how many volume it's occupying. So we can first discuss how many volume it is occupying. And since we are going to just use a scaling relationship, we don't need to worry too much about all these specific constant in front of it. So that we can visualize the density of a polymer chain will be proportional to n will be number of the chain, okay? R power of 3, R would be the radius of your inside a volume R, okay, radius. So you can think about here, that's R. We have a certain polymer sitting inside it. That would be the bond. And so that's basically what's the density of it, right? N divided by R power of 3. And this very much resembles what I mentioned. In the New York City, your chances of seeing in other people is much, much higher because population density is much bigger than in the countryside. And assuming we know that a repulsive energy would be equals to a constant. The constant can be defined as V kT. K is a Boltzmann constant, okay? T is just temperature. V is just a factor that defines what is each individual molecular's energy, okay? So we can call it cost of contact energy. And kT is basically unit of energy. Sometimes people put a B there. kBT is the same. So this term defines what would be the cost of ion touching with another person. What's the energy cost? So how about total system energy cost? Because we have also talked about for each bond there's n segments there, so there's n carbon along it. So then we can call it total energy of cost in terms of energy available to make the system expand will be kBT multiplied by this unit energy, and this would be the density we have talked about, the density term, and number of segments was inside one unit area. Okay, so this now describes what is roughly the energy causing the polymer chain to expand within the unit volume. You got the density term as shown here, how many your polymer chain possibly within that unit volume. You got a number of bonds within it, and that would be the cost of individual contacts. So multiply by total possibility, total number of bonds, that will be the total energy available for the system to expand. If there's nothing holding it together, it will keep expanding, right? But what is the reason that we have the system has the forces to hold it together? Okay, so anyone have any answer? Because this is not talked about in the textbook. You probably won't be even to know. But guess what is possibility? Okay, one by one. Maybe Kundu? Yeah, you can speak first, then John.
Thank you. So you're asking for if the polymer is in a good solvent, right?
Yeah, it will be in a good solvent.
We're thinking maybe how about the polymer with the solvent? Maybe they don't like each other, and maybe they want to stay together rather than discuss.
Yeah, that's not really applied to this particular problem. We are discussing what kind of force is holding the polymer together without continuous swirling nonstop, right? We know there's a swirling force is due to the repulsive of the polymer chain. John, do you want to give it a try?
Honestly, that was kind of where I was going with it.
So. Okay.
Were you asking about what was holding the chain together as opposed to it falling apart?
Sort of, but don't. Yeah, give it a try, Brian.
All right. So in the case of these polymer chains, it may also have something to do with crystallinity. It may be its ability to form regular arrays. It may be its ability to cross-linking, secondary binding forces. That's what holds the chain in opposition to it being repulsed to each other by substituting groups.
That's not exactly right. This what you talk about in these crystalline domain structure, those are more in the solid state. Okay, when they don't have solvents, they're as sort of solid condensed states. So let me ask you another question. Ask differently. So if you have a polymer coil, what we have described, as you already know, it's coil states for typical flexible polymer, right? We draw many times. Think about this chain end A, this would chain end B, and you're just going to have random structures in between until it's connect. So now, Brian, we're going to do a magic trick. You and me are both going to be cast by a spell. We're going to shrink by 1 billion times. So now I'm going to be a nano man. I can hold in this area, and you can hold in chain end B, and we can start to pull it. And this is the same problem as what we talk about force holding polymer together. The force while the polymer chain, after we stretch it can be straight, so like we show here. But once we release, it will likely to come back to where we start off. And that's the same reason. And anybody under this hint knows why? What's the forces getting the polymer back to the coil state?
Rotation isomeric state. The rotation being fixed.
Yeah, you're close to the answer. Yes, it's a good step. How about the others? Want to give it a shot?
They're sp3 carbon-carbon bonds, so I want to have that 109.5.
Okay. Yeah. Think about big picture. Think about what is the universe is doing. Universe is keep expanding, and for a reason. It's want to reach what? Reach the maximum entropy. That's the same problem here. We are trying to talk about the entropy problem. When in this stage, your entropy is high. In this case, your entropy is low. And first, let me define this, what is entropy, then, because in the next month, we're going to talk a lot about entropy and how does entropy impact your polymer structure and dynamics. So entropy basically means degree of disorder in the system, okay? And you guys may not experience it much, but I'm dealing with entropy increase every day in my house because entropy increase is a spontaneous process. The third thermodynamic law says everything gonna go into high entropy state. Or in other words, or in the layman's language you want to explain to your grandma, that means everything will get in disorder. Disorder, that means your nice kitchen will get, disorder with dishes flying everywhere. You need to put the energy to put it back into order. In my kids' playroom, every day I need to reset it to entropy of 0 because it's always a mess. You have toys everywhere. Same. It's just the nature need to go to high entropy states. So if you look at here, there is quantum mechanics defines your entropy would be equals to K line. Let's call it omega. This omega would be equals to number of possible configurations. Okay, is it what everybody understand what this is? And again, this KB is a Boltzmann constant. It's just a constant value that you don't need to worry about it. And entropy would be directly proportional to number of states your system is possibly to configure to reach. So now look at the top one. In this configuration, in the scenario A, your chain is coiled. There is so many randomness you can reach this end-to-end distance, as we discussed in the previous lecture, right? Your possible states within here is much, much higher than extended chain, because in the extended chain, if I want to take a certain bond angle, it will not reach this state, but it will more likely to reach that state. So that means there is entropy force come into play. If your polymer coils keep expanding, at the same time your entropy is trying to confine to a certain size, then there must be an equilibrium. So now we just need to figure out what would be the forces to holding the polymer together. The forces holding it together, and I think we already discussed in previous few lectures, talk about what is the probability of the chain distribution. So probability is quite tied into this number of possible states. So probability will decrease when your chain is keep extending, right? So we can directly write this entropy term, F, will be proportional to, again, kBT mb squared. Let me explain what this term is. So that tells you what is entropy in the system is R squared will be directly proportional to what is the size of your polymer coil. mb squared will be equilibrium end-to-end distance. So your entropy, which is going to increase, right, with the expansion of your polymer coil, is going to be holding your polymer chain together. So now if we consider the total system energy, it's going to be a linear combination of what is causing it extend, what is causing it to fix it together. So this is entropy. This would be what we have discussed in the very beginning, which would be expulsion force. You can write it quite simply as kBT. The first term will be quite straightforward, right? So now how can we get the equilibrium size of your polymer? Any thoughts? Where your equilibrium polymer coil size can be understood from the balance of the force? This comes down to some simple math. We need to take just the first derivative of force divided by R. If this will be equal to 0, then we know that 2 of the force is balanced. Okay? So we can use that to quickly go through some of the data today. So if we took this approach, we know that if we take first the derivative, so this term would be equals to minus 3 plus 2R divided by mb squared, right? So that's the first derivative with respect to the radius of R. And if we know this if this would be equals to 0, we can rearrange and get what would be the R power of fifths will be roughly equals to n3. So you can see R would be proportional to n divided by 3 divided by 5. So this is quite nice that Fourier series, despite a very simple concept, right, but it successfully was able to predict how much degree of chain expansion you would have in the good solvents. In this case, we know there is repulsion force due to the self-avoiding work effect. Your chain cannot sit on each other. And there is also a second term called entropic spring effect, where you cannot continuously to stretch the chain because entropic force is trying to limit it and it comes back. So those two forces would balance out at a certain radius, And this certain radius, as we calculate out, will be equal to m power of 3/5 or power of 0.6. Well, it was quite amazing 70 years ago without any computers. He was able to use a pen and paper like we did today to estimate, and this matches very well with what we have been able to do, use a more modern computational, they call it a randomized group theory. It's more fancy ways to do such problem using a self-avoiding work. You can ask a computer to self-avoiding work many long distances. They match us very well. But Florey did it by accident. The real expulsion force will not be this high. He overestimated the repulsion term, but meantime he also overestimated the elastic term. But it's a happy accident. Those two canceled out each other. So he got the right answer. At the end, R would be equals of n power of 0.6. That is quite amazing. So I think this explains pretty well. Now everybody understands what is in polymer in idealized cases and in real cases in good solids. And I believe I also mentioned a couple times what would be the polymer behave in idealized chain in real case, and they will be two specialized cases. So one is polymer in melt. Okay, why polymer in melt is an interesting question. We can also explain it in a polymer physics perspective. In the polymer melt, why does it behave in idealized chain? Anyone want to give it a thought? Anyone want to give it a try? We can also think along the two forces we just discussed in terms of repulsive force and attractive force. And we know this will be, we can say, behave like ideal chain. Okay, but the reason is why? Yeah, good answer. Yeah, very good answer, Jaeyoung. Now, we can also give a more visualized way to think about. Now I'm going to give an interesting example that I don't think this would happen in the Western country. But when I grew up, we lived in Shanghai. And Shanghai is a mega city. You got like 200 million people living in a very crowded area. And it's very bad traveling in the morning and the evening when you want to commute. And a lot of people opt out to go into a subway, but it was so packed that you can also see in Tokyo, and they would have officers standing outside out the door. His job is to push you so that door can close. So you can see that each compartment is so packed. That's related very well to what we're going to talk about in polymer in melt. Okay, James, please mute yourself. There's echo. So in this case, as a human being, you can tell if your body part is touching others or not. Right? But in a polymer chain, it's happening at the same phenomenon that they don't have a conscious like we do. They cannot tell if they're touching themselves or if they're touching another polymer chain because they're so condensed. It's a melt. It's a polymer melt. So every polymer chain is wiggled together. If you can tell if yourself is an individual chain, then you can contract and make a compact globular, right? You will be condensed in one phase. You wouldn't necessarily reach out to expand as much as possible. That would be stupid in a crowded subway. For polymer chain, it doesn't have the mind, so it cannot tell if it's exposing or expanding itself to touching another polymer chain or not. So your repulsive force will still be there, right? When we talk about repulsive term. But for a given moment, let's draw a polymer random chain. Let me see if I can change a color of my drawing pencil to represent a second chain. Should be able to. All right, perfect. So now we should have, oh no, it's still red. Oh, we're gonna just draw it. Don't have a green one. But this would be, the middle one would be the second chain. If the polymer chain is here, it will get a repulsive force from its neighboring chain, but it would also get a repulsive force from another polymer chain at the same time. So those two repulsive forces will happen to cancel out each other for every single given polymer chain. Okay? So when you don't have repulsive force, or for that polymer, it exists, but it happened to be one got pushed in front and the other got pushed in the back. So this force naturally cancels out each other. And this is the reason that polymer in the melt, despite there is self-avoiding work or there is exclusion effect, but it was able to still adopt an idealized chain model. Okay? And we're also going to discuss a polymer inside a solvent. Okay, what is Seda solvent, by the way? It's not like a magic solvent or fancy solvent. Historically, people just call it Seda solvent, and basically this is explains a solvent that has slightly lower solubility than good solvent, and this happens to allows polymer to adopt idealized chain conformation. Okay, so that means your R will be again equals to n power of 0.5. And this is what we also talk about. The solvent quality can impact your polymer. If it's a bad solvent, your polymer will be shrink. And going back to what we discussed here in this, we see the Rg for a polymer in a good solvent will be about 15 times. X is a number, and in the idealized polymer, it's only 10 times. So you are talking about 50% of volume expansion. But if you keep adding bad solvent in this particular solvent, polymer is going to shrink. And as you can imagine, it will pass where it's idealized chain. If you add too much, it will collapse down to a globular, okay? If you add too little, it will still be bigger than what you had in idealized chain. But you could happen to have a polymer configuration behave exactly the same as idealized chain. And at that point, we call that solvent is Seda solvent. And Seda solvent can be a single solvent or can be a combination of two solvents, a good and bad, at a certain mixed ratio until they reaches what they show as idealized chain behavior. All right? So those are two extreme cases. In reality, people measure a lot of melt. Zeta solvent, to be honest, is quite hard to reach exactly that point. People only discovered, purposely 10, 20 of those solvents for polymer. For example, toluene, as you will see in the textbook, it will have a given temperature and a given solvent combination behave like that. And temperature will impact because solubility of the polymer is dependent on temperature. Higher in temperature, lower temperature will impact its chain conformation as well. But that should wrap up what we want to discuss in all the models and all the discussion we had in the polymer chain and polymer configuration. We discussed good solvent, bad solvent, solvents in between, and rigid chain, flexible chain, and all kind of different chain configuration. And this should give you a good start for understanding several of polymer physics problem. Okay. So what's the plan next is we're gonna do Thursday. We're gonna go through all the homeworks. We got about 20 of them. So we're gonna discuss those 20 problems ish, and we're gonna go through one by one and do a live Q&A in this class again at 9:30. Hopefully we have enough time to go through all of them. Then next Tuesday we're gonna have a test. So I'm gonna send out a PDF to everybody, and it will be an open textbook test. But don't use Google. That will be not a good way. It will be again about 1 hour test. So for some of you need extra time, feel free to email me. Give yourself a little bit extra time. So in the next chapter, we're going to go into something totally different. There's no more chain configuration, etc. We're going to only discuss the polymer in solution and phase behavior of polymer. And those will be quite different. And as I mentioned, we're going to study a Flory-Huggins parameter at the beginning. And Flory-Huggins parameter is very interesting parameter. It's like most famous person. Most famous concept in the polymer physics field, so you have to get ready to learn that. And we're gonna again spend about 1 month, so that will cover chapter 7, thermodynamics of the polymer solution. So if you have not started reading it, so you can after your test you can start reading about that, understand those phase behavior. So I'm going to wrap up today's synchronized lecture, and anybody have any question for today's lecture?
Do you have any recommendation for preparing for the test? Because we've already gone through the problems in the book. Is there anything else that you'd suggest we...
I think that if you go through the problem with the book, that will be quite amazing. And the other thing I suggest to you to study is basically read a couple times what has been discussed inside the chain polymer conformation. This chapter 6, is all you need. And my test will not exceed the boundary of that textbook. But as I mentioned, I do appreciate people can go deeper in the textbook. So we sort of didn't discuss several mathematical deductions of how we get a certain relationship in equation. For example, we omitted what we discussed. What we could discuss is how do we get C infinity in terms of free rotation chain, and how do we get that characteristic ratio of cosine theta plus 1 divided by cosine theta minus 1. That could be a bonus question for everybody in the test. Okay, so you know there will be some extra, but if you don't know, that's fine. All right, so the main text will be 100 points, and there's 10 points of bonus point. Okay, so any other questions?
Could you go back to some previous slides, sir?
Yes.
Like starting with the one on total energy.
Yeah, so right here.
Okay. I meant the one. I'm sorry. I meant the one on total. Not the one on total energy, like the one on.
Oh, okay. So is it here?
That one.
Okay.
Yes, so what's that constant that says that's V?
It's basically, if you have some contact in the energy, it's not going to be kBT. kBT is basically a unit energy. That's what we said in terms of, let's say, if I go to a grocery store, that's how many miles we need to drive. So kBT is like equals to 1 mile. That's a unit energy. Okay, that cost of contact energy, V, is just basically a constant. We prescribe it to what energy we're going to have if we have a certain contact. You can visualize it as just a constant.
And then you multiply that together to get total energy of expansion.
Yeah, that's exactly right. So total energy expansion, let me walk you through. So this kBT multiplied by V, that's what we have discussed. That's basically the unit energy per contact. If I have one polymer bond, carbon bond contact with another one, that will be how much energy I need to cost it to contact, okay? That is kBT multiplied by V. And divided by R3 is basically density of you have a single carbon hitting with another one within the unit volume. That's R3 is unit volume. As we know, the volume for a sphere is 3/4 multiplied by pi and multiplied by cubic of R, right? So N is number of carbons along it. So this defines what's the density of fuel for a single carbon hitting another carbon. And for this given unit volume, we have how many number of carbons? That will be equals to N. So if you multiply all the terms together, that defines all the expansion force within the system.
So multiplying the cost of contact energy, the density, and the number of molecules gives you the expansion energy.
Yeah, exactly, Brian.
Okay. Then I just forgot that I just that you went to I just that you I didn't get just write down everything on the slide. So do you go to the next slide, sir?
Yeah, no problem.
Thank you.
Let me make it bigger so you can see it. That's entropy of expansion.
Yes, sir.
I'll upload this to the Canvas so you can have all these notes. And I think John mentioned about the slide. John, I was able to upload it as well as all the other Q&A lecture notes. And have you able to see them? It's uploaded as a PowerPoint format. Okay, great.
Yes, sir.
Okay, if there's no more question, I'm gonna wrap up. And everybody, I feel like the second homework is not everybody turned in, and not everybody got everything right. So we're gonna have a fun discussion this Thursday. So please give it a final push for the last homeworks, and please send it in on Thursday, and we can go through all the homeworks on Thursday. Okay.
Yes, sir.
All right. With that, I'm gonna wrap up. And then everybody stay safe. I was thought the hurricane will be worse, but looks like we are very lucky. It went to the west.